Hello, this is the course of data structure and algorithm, and I would like to continue the course with the idea of graph. Okay, so last time we already learned about graph. Oh, yeah, I have got my video. Okay, so in the first video, we learned about the graph, and we learned that the graph contains the vertex and edges. And for this video, we will learn about the algorithms that you can apply when you're dealing with the graph. One of the concept about the graph that you can apply in the algorithm is what we call as the depth first search. So today we are going to learn what is depth first search, and in some literature you can just call it as DFS. Okay? So I took the content from the book that I already recommend to you as the reference, which is the Data Structures and Algorithms in Python. So yeah, we are going to learn about the concept of the DFS, and then the DFS algorithms with the Python implementation. And yeah, you can learn about the properties of the DFS. So this chapter is about the DFS. Before we go deeper about the DFS, I would like to uh, give you one more definition about subgraph. You know, the graph is an object that has vertex and edges. We can have what we call as a subgraph. Okay, the subgraph means it is the graph. It is a graph G. Okay. A subgraph S of a graph G is a graph such that, okay, so this is the condition, the vertices of S are a subset of the vertices of G, and the edges of S are a subset of the edges of G. So you know subset, okay? So let's see. This is a graph. Okay, you have the blue color. The blue color. Okay. This the full of this one is a graph. Okay, and we call this is a subgraph. Okay, so the line, the full line connector between the vertex, we call it. This is a subgraph because the vertices are the subset of the vertices of the graph G. Okay? So this is the graph G, and this is the subgraph S. Okay? So the vertices in S is the vertices of S are the subset of the vertices of G, and the edges of S are the subset of the edges of G. Okay? So that's the definition. We can have another definition, what we call as spanning. Is a spanning subgraph of G is a subgraph that contains all the vertices of G. Okay, if here you have this one is a graph. Okay, so this is a graph, and what we want to know from the spanning, okay, so spanning subgraph, if it contains the all vertices in G. So this is the vertices, this is the vertices, this is the vertices, this is the vertices, yeah, this is the vertex. Okay, so those are the vertices of graph G, but they don't have these edges, so they don't have these edges. So we call this is the spanning subgraph. So it is a subgraph. All the vertices are the same with the G. Okay? All the vertices are the same with G, but the edges, some of them are not the same. Okay. The connectivity is also another kind of definition for graph. So a graph is connected if there is a path between every pair of the vertices. Let's say you can see this is a graph. Okay, so this is a graph, and we call it this a connected subgraph because all the vertices or of the vertices are connected. Okay, so there is no unconnected vertex. We call it a connected component of a graph. Okay, we call it a connected component of a graph is a maximal connected subgraph of G. So if we have a graph, this one is a graph. So this graph is non-connected. Okay, there is one here. It is not connected to the other vertex. So we call this is a non-connected graph. Okay? It is a non-connected graph because it is not connected with two connected components. So we call this is the connected components. So the first, yeah, this is the first connected component, and this is the second connected component. So there are two connected components. We can have also another definition. We call it trees and forests. A free. Okay, so yeah, in some literature they call it free. Okay, so it's a forest tree. Okay, but yeah, just say it's tree. Okay, so be careful when you say this is tree. Don't be confused with the tree that you already learned in the previous chapter. So the tree here is the tree based on the graph. Okay, so what is the tree based on the graph? It is an undirected graph. Okay, you know graph. We learn about the directed graph and undirected graph. And for this chapter, we will learn more about the undirected graph. Let's suppose we have the undirected graph T such that T is connected. Okay, you know, connected graph. So all the vertex should be connected, and there will be no cycles. Okay, so T is a tree with no cycle. So if there is no cycle, then we can say it is a tree if the T is also connected. So this definition of tree is different from the one of a rooted tree. Okay, so in the chapter 7, yeah, it was before the mid exam. You learn about the tree, and it was the rooted tree. Okay, so this tree is based on a graph. We can have another definition from the graph, which is a forest. So a forest is an undirected graph without cycles. Okay, so tree and forest, they have no cycles. And if it is a tree, then it should be connected. But if it is a forest, then there might be some unconnected. Okay, so this is not connected, so this is not connected, and this is also not connected. Okay, so the connected components of a forest are trees. It means this is a tree, okay, and then this is a tree, and yeah, actually this is also another tree, but yeah, actually it's not connected, so it's not, I cannot say this is a tree, but at least those two are trees. Yeah. The spanning trees and forests is also another thing that we can learn. Okay, what is a spanning tree? We call a spanning tree the spanning tree of a connected graph. Okay, we have a graph like this one. If it is a graph, then we can have a spanning tree, and the spanning tree is a spanning subgraph. Okay, so a spanning tree of a connected graph is a spanning subgraph that is a tree. So we can see this one. If we have a graph, so the spanning tree is another connected. Okay? So this is the vertex, this is the vertex, this is the vertex, this is the vertex, and all should be connected. Okay, you know the tree. What is the definition of tree? There are two. It is connected and there is no cycle. So a spanning tree is a connected graph that is a spanning subgraph that is tree. And if it is a spanning tree, So the spanning tree is unique unless the graph is a tree. Okay, so a spanning tree is not unique. So you can have many alternatives of making your spanning tree. And the spanning tree have application to the design of the communication network. So let's say I want to connect to a particular network, then you can just find what is the nearest network and what is the possible network for building network. A spanning forest, okay, there is another term, it's called the spanning forest of a graph, is a spanning subgraph that is a forest. Okay, so basically it's the same with the spanning tree. A spanning tree is a connected graph that is a spanning subgraph that is a tree. And if it is a spanning forest of a graph, it is a spanning subgraph that is a forest. So if you check this one, this is forest. Okay, so the forest here is, okay, so the forest here is undirected graph without cycles. So yeah, at least you will satisfy with the requirement with this no cycle. So it is a forest. So when you deal with the spanning forest, it means it is a spanning subgraph that is a forest. So it's there are some vertex which has no connection each other, and there is no cycle. So we call this is the spanning forest. Now we are going to learn more about what we call as the depth first search. So the title of this chapter is about the depth first search. DFS is a general technique for traversing a graph. If you still remember traverse. So in the tree, you learn about the pre-order traversal, post-order traversal, and in-order traversal. So the traversal here is the way to visit the node, and DFS is one of the traversal that follows this procedure. So first, visit all the vertices and edges of G, and then determines whether G is connected and computes the connected component of G, and then computes a spanning forest of G. Okay. So if you have your mind about the terminology of the graph, so you know the connected graph, you know the connected components, and you know the spanning forest, then you can understand this idea of the algorithm. DFS on a graph with n vertices and m edges, it will take O n plus m. Okay, so n plus m. There will be no more than n plus m for the DFS. DFS can be further extended to solve other graph problems. For example, you want to find and report a path between two given vertices, or you want to find a cycle in the graph. So you can use DFS. DFS is to graph what Euler-Tor is to binary trees. So if you still remember the Euler-Tor in the chapter of trees, so it is about the trees. Okay, so it's about the binary trees, but the depth first search actually it is a part of graph. So please don't be confused with the depth versus and the Euler-Tor. This is the algorithm that we are going to use to understand the DFS. So we have the graph G, okay, and then the output is labeling of the edges of G as discovery edges and back edges. Okay, now let's say I just say that discovery edges is like D, okay, and then back edges as B. Okay, and for all U in G vertices, so it means if you know all the vertex, so for all vertex, set the label unexplored. Okay, first all of them are unexplored, and then for all E in the edges, set also them as unexplored. and you will have the algorithm for all v which is in the element of the vertex, and check if the label of the vertex is unexplored, then do DFS. Okay, what is DFS? In this DFS we have G and V. Okay, so what is G and V? We have this is a graph, and then V is the vertex, and the output will be the label of the graph in the connected component of V as discovery edges and back edges. Okay, so as I mentioned to you, I will just give this one T, and then I will give you this one as P. When you do the visit to a particular V or vertex, set the label visited. And then for all E, which is the incident edges. Do you know what is incident edges? So it is the edges that is connected to the particular V. Maybe I will just explain with the example here. Yeah. So this is the code in Python. Let me explain with this one. Let's suppose I have A, B, C, D, E. Okay, so the blue color is the node which has not been visited. So if I can say, okay, A, okay, and then I have B, and then I have C, and then I have D, and then I have E. Okay, so those 5 nodes, they are unexplored. Okay, unexplored, 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 and unexplored. Okay, so this is the step. Okay, so set all the label as unexplored, and the next is set all the edges unexplored. So it means you can just put this node as unexplored. Okay, this all nodes are unexplored. This is unexplored, this is unexplored, this is unexplored, this is unexplored, and this is also unexplored. Okay, now what you're going to do next is you will check the first label, which is, let's say I start from A. Okay, so if A is unexplored, then do the DFS. Now we set the label V because starting from A, so set the label as visited. So I will change this one to visited. Okay, because it is already visited. Now let's check for all E. For all E, which is the incident edges of V, now you can see what is the incident. So this is the incident. Okay, 1, 2, and then 3, and then 4. Okay, so there are 4 incident edges. Maybe it's better to okay, so it's better to erase this one. Okay, now we have this one. This one is the incident, this is the incident, and then this is the incident. Now 4 incident edges, and then what we will do next is to check if the label E is unexplored, then let's check what is the opposite of V comma E. Okay, so yeah, because this edge is unexplored, then we want to check what is the opposite. What is the opposite of A and this edge? We can see P. Okay, so here P will be noted, and then let's see, get label of P. Okay, and B is unexplored. If now it is because we have P. Okay, so P is unexplored. Okay, please don't mind with this one. Maybe I can change this one into the Oh, I need to change this into the blue color, maybe. Let me change to blue for this one. This is the D, okay, and then this is the P with blue, okay, and I will use red to indicate the note. So this is the P, and is in the red color because it is representing the note, and I want to know if the P is unexplored. If P unexplored, yes, P is unexplored, then set the label E as discovery, okay, and then DFS GW. Oh, it is interesting. So we will set the E. Now this one is discover, okay. This I think I need to use the blue color. Now it is D. Yeah, we discover this X, and then we want to do the DFS G comma W. So in this case, the W equals to P. So we want to go to the P. Okay, so we want to go back to this DFS. Now we have the same G and but the V equals to P. So we have another input, and then what is the output? So to set label, what is the set label? Now we have the label which is P and set it as the visited. So here let's put the variable node P as visited, and after we have the visited here, okay, the same with the previous one, we want to check for all ads in the incidence of V. So because now we are checking the P, so we check the all edges of P. So all edges of P is okay, only one. Okay, so we want to check this, and then we want to get the label E. E is unexplored, yes, because it's the first time. Okay, so it's unexplored, and we want to get the opposite of V comma E. What is the opposite of P and in the E? So the note will be, okay, I need to erase. So the note will be, now it is changing to C. Okay, so now we're checking C. Yeah, we're checking C. Okay, so we're checking the C. And if you know about the C, oh, I'm sorry, I'm not that consistent with the, yeah, this should be C. So if you know that C is the opposite of P, so let's check, get the label of W. So W is C, it is unexplored? Yes, because it is unexplored, then you will set the label E as discovery. Okay, so you will set the label E as discovery. So you will have this label as D. So this is another discovery. Okay, after we have this one discovered, we have this one. Okay, so this node and this node has been discovered. Okay, and yeah, what we are going to check next is, okay, DFS G comma W. What is the W? W is C. So now we are changing this node, not P anymore, but now it becomes C. So let's see again. We have the DFS G comma C. C is the node, and let's put the label V as visited. So change the label C as visited, and then after I know that this C has been visited, what you're going to do next is to check all the incidents of the ads, all the incidents from C. So you will go to the possible line here. Okay, now you will check. if the label is unexplored, okay, yeah, the label E is not explored, okay, then we go. So W is the opposite of, okay, because it is a new one again, then I will just erase this one, okay. So the now we have C as the V. So C, I want to know what is the opposite of C. The opposite of C is A, okay. Now I want to check if the label of W is unexplored. Hey, what is A? A has been visited. Now it's already V. So it is false. Okay, it it does not satisfy with this. It does not satisfy with this constraint. Then we will go to the else. What is the else? The else is set label E as back. Then yeah, you can see this one. Now it is back. Okay, so this is back. So the back edge is represented by the dash line, and discovery edge will be represented with the arrow because it is a back edge. Okay, then you will check what next. After you finish this one, you will go to the other E. Okay, you will go to the other E, which is another edge, and after you check the other edge, you need to get the label. Okay, whether the label is unexplored, and then let's check the opposite of C. Okay, after I know that this is the back edge, so I can check this possibility. So this is the line, okay, and then I want to know the opposite. What is the opposite? Okay, the opposite is D. So we know the opposite now is not A, but the opposite now becomes D. Now get the label W. What is W? W is D. Is it unexplored? Oh yes, D is unexplored. So this is the unexplored. So we change this into, oh sorry, not yet. So we just set the label E as discovery, and then go to DFS G comma W, and it changed to D. Okay. So it means we will change this line into discover. Okay, we will change this line into discover. Okay, this is discover, this is discover, and this is back edge. Okay, so you will have this one as D. Okay, you will have this one as B, D, this one B, and then this one D, and the same. Okay, after I know D, and I will check the possible edges. I will check the possible edges. So we have D because D has set the discovery. So I want to go to the DFS again, G comma W. So here is D, and then D will be set as visited. So D will be set as visited. So the D now becomes visited, and after D is visited, you will check. Okay, if D will be the okay, when D has been set as visited, you will go another loop to check all the possibility of the incident edges of D. Okay, so now we change to D. So the all possible edges of D are this one. Okay, there's one possible for this line. Okay, once you get this E, you want to check whether the label is unexplored. Yes, it is unexplored. Okay, because it is unexplored, so you will to check what is the next step. If it is unexplored, then you want to know the opposite. The opposite for the D is A. Okay, and then you want to check if the label W, which is A, is unexplored to this one. But actually, we already visit the A. Because we already visit the A, then you will set the label E as back. So again, you will set the H here as back. Okay. After you have the back here, what happened? Is there any other E from D? Okay, because there is no other E from D, then you will finish the for loop. Okay, and when you finish the for loop here, because there is no other incident edges of T, you finish the for loop and then it will return back to the previous node. What is the previous node? The previous node is the C. Okay, so after you have the C, and then you will go to the next stage. So you want to check another edge. Okay, what is the another edge? Yeah, after I check the after I go to D and D cannot find any other edges, so it will return back to C, and then I want to check what is the alternative of the edge from C. So we can see there is an alternative to E. Okay, so we will check the edge to E. What is this one? What is this edge? And when you check this one, okay, the E is the label of E is unexplored. If the label of C is unexplored, yes, it is unexplored, then check what is the opposite of C. Okay, so what is the opposite of C? The opposite of C is E. Okay, and then you want to know the label E is unexplored. Yes, it is true. So the HE will be set as discovery. So now we will set this one as a discovery. Okay, so we'll set this one as discovery, and then go to the DFSG, W. So when you do the DFSG, W, again, we will go to this part, and then you will check based on the E. Okay, and again the set label. So the set label will be E, and E will be set as visited. So it will be set as visited. After all the visited, yeah. So actually, if you already finished with this E, yeah, you will check another edge. Edge is yeah, another edge to get the incident edges of E. Okay, what is the incident edges of E? Okay, E has one edge to A. Okay, so E has one edge to A, and then after you check this one, the label E is unexplored, so you will get the opposite of E. The opposite of E is A. Okay, because the opposite of E is A, and then you want to check again because it is A. So A is unexplored. No. Okay, so set the label of E as back. So now we'll check again to this one. Yeah, this one will be pointed as back. Okay, so the final edge are like this one. So this is B, this is B, this is B, and then this is D, and then this is D, and then this is D. So D means discover. Okay, D means discovery edge, and B means back edge. Okay, so this is the result. You can use this DFS for the maze. Okay, the maze traversal. So the maze traversal is one of the application if you want to go from one point. Okay, so let's say this is the point of origin, and then you want to go to this destination. Okay, so when you learn this one, then you will check the path. Okay, let's say this is the possible path. Okay, and then you will check and then yeah, you will go something until you finish this one. Okay, so if you are by a chance you didn't choose the right path, okay, for example, okay, you find a block, then you will return back to the previous intersection, and then you will choose another way. And then let's say if I go to this one, oh, then yeah, it's not the block, so it will return back here, so it will just make another loop. And then yeah, if you go to this one and then you find a block, so it will return back. You will go to this one if you find a block, and then it will return back. So yeah, every time you find like a block, or yeah, in the previous example, if you've already explored those edge and the node, then you will return back, and then you will find another edge and another node to visit. Okay. So the properties of DFS, there are two. So the property one is the FS visit all the vertices and edges in the connected component of V. And the property 2 is the discovery edges labeled by DFS, which is G, V, and it forms a spanning tree of the connected component V. Okay, so those two properties are the properties of DFS. The analysis of DFS, if you set or get the vertex or the edge label, it takes one time. Okay, so you just put the explore, unexplore. Okay, so for the first time it is unexplored, and then when you visit the node, you set it as visited. Each vertex is labeled twice. Okay, so you need only to set as explored and visited. For each edge, it's labeled twice, which is unexplored and discovery or back. Okay. When you have the incident edges, okay, you know that the incident edges is a kind of loop, and it is called once for each vertex. So if you already have the incident edges, then it will at least called by one time. So the DFS will run for n plus m, okay, because yeah, after you do with all the vertices, you will just add only one or two or three edges. So that's why we have the O n plus m. Recall that the degree V, okay, so the summation of the degree V equals to 2m. So you already know from the properties of graph. We can do with the path finding, okay. The path finding here is another issue for the shortest path, okay. If you are doing with the DFS, okay, so the DFS here we have the G, which is the graph, and the U, okay, so we have the U as the first vertex and then the Z as the second vertex. So the U is the starting vertex, and we want to go to the destination, which is the Z. Okay. The idea is still the same with the DFS, but now we are making a kind of route. Yeah. So the first time we want to set the label V as visited. Okay, V and Z. So V is the origin and Z is the destination. If you still remember, we use stack. Okay, so we use the stack as to keep track of the path between the start vertex and the current vertex. So let's push V. And then we want to know if V equal to Z. So if the current vertex equals to the destination, then let's return the element of the stack. Okay, so it means yeah, you will finish the finding the path. But if it is not equal to the destination, let's check. First, you will just do the loop for all the edges. Okay, I think it's the same with the previous DFS, but it is a path. So you already know a path Okay, a path, you need to visit every node. Okay, if it is a simple path, then every single node should be just passed by one time. If it is not simple path, then it means there will be more than one node that has been visited. So in this case, it is only just path. Okay, so you don't need to worry about whether it is a simple path or not simple path. But at least is a path, you need to have a route from one node to another node, and you need to check whether the label is unexplored. Okay, if it is unexplored, you will see the opposite. The opposite, it means the vertex that is connected through the E to another node. And when we have the W, we will check what is the label. If the label is unexplored, then again you set the label E as discovery. Now the only difference between the path DFS and the DFS is about the stack. So we use the stack here, we use the stack here. Okay, so once you put this stack, I know that this W has not been visited. Because it is not visited, so I would like to put this E as the edge for the next trip. Okay, so after I know the next trip with this E, I would like to make the path DFS G, W, and Z. Okay, so the W will be the next node. Okay, so for example, if I have like this one, okay, I have this one, so if I go this one, I go this one, and I go this one. Okay, so if you like say this is the A, and then I want to go to D. Okay, so after I check this one, and then I will go to the next node, which is W. So W is like this B, and then again I will just use the B comma Z. So the destination is D. If I know the C is the opposite, then I will go to C, and then I will check if the edge is unexplored. Then yeah, you will push the edge to the stack, and then again you will check the path DFS GWZ. So C is the node, and then the destination is D. So and so on, then it will be repeated until you satisfy the condition with this V equals to Z. And every time you cannot find the node, if every time you cannot get the label unexplored, you will set the label of the edge with back. Okay, so this pathfinding actually is similar with the DFS, but you apply the stack. You apply the stack. You apply the stack here. It is the stack inside of this E is to give the stack for the edge. And after you finish with this pop and push in the edge, you can go back to the original stack, which is for the vertex. Okay, so this is the V, and this is also the stack for V. Okay, the cycle finding, yeah, you know the cycle in the concept of graph. Yeah, we have the node, the origin node will be equal to the destination node. So if you go from Seoul and then you want to go to Daejeon, and then you go to Suwon, and then you go to Incheon, and then you need to return back to Seoul. Okay, because the origin is Seoul, then you need to go back again to Seoul. So in that case, okay, the DFS, it can find a simple cycle. Okay, so it can find a simple cycle using the template method pattern. Again, we will use stack to keep track the path between the start vertex and the current vertex. And for back edge. Okay, back edge is the when you return back to a node that has been visited, so it can be written as the cycle of the portion of the stack. So if you see this one, this is the same with two parameters, g, which is the graph, and then v, and then z. And then you want to set the label v as visited for first time, and then you put it as a stack. And yeah, after you have the v as in the first stack of the vertex, you want to check the edge. Okay, what is the edge here? Yeah, this is the incident edges. And after you know the incident edges, again you want to check whether the edge is unexplored. If it is unexplored, you want to check the opposite. Okay, the opposite, which is the opposite of the vertex. And then if the opposite is available, you just push the E. Yes, you just push the edge. And then check if the label of the particular node is unexplored. If it is unexplored, then just make the E as discovery. And then do the recursive path DFS. Okay. So this path DFS is the part of this one. So you need to find the path. Okay. After you find the path, you will go. After you finish with all those paths here. Okay. So this is the unexplored. Okay. For the this is the unexplored for the ads. If it is unexplored all this one, then yeah, you can you still be able to visit the other products. But if the label is not explored or it is already visited, then you will go here. Okay. So what is here? So this if, this else, or if it is already visited, so you need to get the empty stack. Okay. The empty stack, it is to know whether you already returning to the destination, or if you are returning to the origin, then yeah, it's satisfied. But if it is not the same with the origin, then you need to put all the things in the T until the origin. Okay, until the origin is the same with the destination. So in this new stack, you will repeat. Okay? Every time you have the stack, you will pop. So the latest node, it will be pop up. And then after you pop, you put the O into the T until O equals to W. Okay? So the W means the node that is the opposite one. And then finally, you will return the elements of T. So if you already know that O already equals to the W, then you will return all the element of the stack. So those one is the this is the process in order to get the cycle. Okay? After you know the V equals to Z, okay, then yeah, you just pop all the V that has been explored before. Okay, so the concept is the same like this one. Okay, if we are using DFS, you will check the V. So you will check the V that is equal to Z. Okay, so if you are using the PetDFS, it means you want to go to all the nodes in the graph. So here you want to go from the W to Z. Okay. But yeah, the vertex for this Z, actually, yeah, it is the same, okay, with the first vertex, which is the V. Okay. So as I mentioned this one, as soon as the back edge, as soon as the back edge V, W is encountered, so we return the cycle as the portion of the stack from the top to the vertex W. So that's why we have this one. Okay, so we will return back to the W, and then we got all the elements in order to check whether it is a cycle or not. Okay, so yeah, I think that's all for the DFS. The concept is a little bit long, but actually when you try to apply that one in the Python code, it's not that long. So it's not that difficult to understand in the Python code. Okay. I guess I already give you one of the code in the Python, which is here one. Okay, so when you do the DFS, you will have the graph, and then you will give the U. U means the vertex, okay, and then you want to put as the discover. So for every E is the edge in the incident edges of U, then you will check if V, okay, the V is the okay, V is the opposite of the U, and if V is not discovered, then discover V equals to E, and then again DFS, DFS, DFS. Okay, so this kind of implementation is taking about n plus m. Okay, so you, even though you know that this is a for loop, okay, so there is one question from the student when you do the exam. There is one question: why, even though we have the for loop, okay, why when we have the for loop, the computational time is not n? Okay. There's one question that the student asked me about one section in the chapter before the mid exam. So why we have the for loop and why we have the while loop, even though it is while, but it is not n? And one example, if you still remember, it is about the span. I think there's one example about span number 1 and then span number 2. Okay, so yeah, if you explore that one, for a for loop doesn't always represent n. If there will be a data structure that you can apply, for example, if you apply stack or if you apply queue, then it can be converted into only a linear manner. Okay, so it can be only n or it can be m. Okay, I guess yeah, I will finish the lecture in this part. So hopefully you can understand what I want to say about the DFS, and in next chapter I will explain about the BFS or breadth first search, and after that I will give you some kind of practice to make you understand about what is DFS and what is BFS. Okay, so thank you very much for listening, and see you on the next video.